All right. Just check. Yeah, that's on you. Cool. All right. Begin recording. All right. Well, it'll be fine, I'm sure. So we have been looking at a couple of properties of functions. Today we're going to be looking at our first very specific example of functions. Again, sequencing is a little bit weird here. I would have rather gotten a few more properties under our belt. But the good news is that this function that we are going to be looking at is one that is very, very well studied. This should be kind of everyone's wheelhouse at this point, is figuring out things relating to this kind of function. Today we are going to be looking at linear functions. So let's say we have two different points here. We will call this point here x1, y1, some generic point, and another point here, which is x2, y2. There are a bunch of different ways that we can move between these 2 points. The way that we are going to be focused on is going to be with a straight line. So connecting these 2 points, our straight line here. And the thing to note about this particular function and functions that all fall under this class is that they are all characterized by having a constant, what we call rate of change, more casually known as a constant slope. That is to say, it doesn't matter what 2 points I pick as a start point and an end point. I can always kind of run at a similar speed through those 2 points at a constant, again, this kind of rate of change. So here, linear function, a function with a constant slope, or an idea that we will expand a little bit more in the future, a constant rate of change. Now we have a couple of different ways to kind of think about slope. That could be formulaic, it could be descriptive, what have you. What is slope? What do we know about the slope of a line? Okay, so one way that we have to define it is that it is some kind of notion rise over run. So how far our function increases as we slide along our x values. Fantastic. How else do we define slope? What else is slope? Yeah, fantastic. So taking this rise over run idea, turning it into something maybe a little bit more concrete, we say that this is also y2 minus y1 over x2 minus x1. Essentially, rather than memorizing this, I think a really good way to think about this is how much has our y changed over how much has our x changed. The way we might express that, delta y over delta x, change in my y per some kind of change in my x. Right. Okay, so linear function defined as a function that has...
This is the final call for laptop deployment. If you have any students in your classroom at this time who have not been issued a laptop, please send them to the library for deployment. Thank you.
All right. Okay, so linear functions defined by their slope. Slope, we now have this lovely formula for it. And then alongside that, there is also the form for a line, which is the one of the like 3 things that I hope that you remember coming out of your high school math education. What is our most generic, most used equation for, I guess not most generic, but our most used equation for a line? Y equals mx plus b. Fantastic. This is our slope intercept form, y equals mx plus b, where our m here represents that slope that we just said, and b here representing the y-intercept, or in other words, looking at a graph like this, b representing the point at which we intersect with the y-axis. So the value, the y value for that particular point, the point itself, of course, being the point 0, comma, b, that y-intercept. All right. Fantastic. Now, y equals mx plus b, good formula, fair enough. It is the one that I feel like most people kind of default to. And I feel like in part it is because a lot of people don't want to memorize the admittedly lengthier, slightly more complicated other formula that goes along. So there's the slope-intercept form, which is y equals mx plus b, and then there is the point-slope form. And to some degree, I understand it, but I also feel like that hesitancy to really work with this other form kind of undercuts a couple of things that would make this even easier than it already is. Right? But to really understand where this kind of comes from, we have to address an issue of notation. This is kind of where I think people get a little bit lost in a lesson like this. And that is kind of the point that I try to make, where I adjust some of the notation that we're going to be working with. In particular, I want us to kind of try and understand what is the difference between a generic point like x comma y, where x and y are both variables, and a point like what we have attached here on our line, x sub 2, y sub 2. Essentially, what do these indices tell us? What are they trying to communicate? Why do I write y2 minus y1 over x2 minus x1? Why the indices? Any guesses? Yeah.
The second point?
Yeah, it's the second point. This is a very, very, very specific value of x paired with a very, very specific value of y. Right? These are not generic. Whatever x2 is, it's fixed at x2. Whatever y2 is, it is fixed at y2. Right? So x2 and y2 can't represent anything other than this one point in space. Okay, that's a problem, not necessarily like a major problem, but if we're trying to come up with a formula that can define an entire line, having it only define 2 points in space is not super helpful for us. All right, now we know that our slope is fixed, that our slope is kind of this constant number. It's always going to be the same. So for our n equal to y2 minus y1 over x2 minus x1, we know that it doesn't matter where we are on the line. This is always going to be true. And so we're going to do something a little bit different here. Rather than talking about the slope for a specific value of x2 and a specific value of y2, we're going to make that just a little bit more generic. We're going to remove the index here. And essentially what that allows us to do is, rather than talking about this particular combination of x and y, we can now instead talk about a generic x and y that is allowed to just move up and down our graph, up and down our line to anywhere we want it to be. All right, so now this point no longer coding for one particular combination now allows us to talk about any possible combination that could live along this line. All right, so very slight adjustment to our slope formula. The slope is still the same, it's still constant, that's what it means to be a line, but just now we want it to talk about any possible point rather than a particular point. Could we also do the same thing for x1 and y1? Sure, we probably could, but it's kind of nice to have like a starting point. It's nice to have an anchor that tells us, hey, we're starting from here, and then we're going to move in this way. So think of here as our start point, and then this decoding how we're going to move, and then somewhere along the lines, think of the x and the y as kind of like the final destinations, and we have like an infinite number of possible final destinations that we would be perfectly happy to end up, right? Anywhere along this line. All right. That being said, still looks a little messy. Fractions are kind of rough. So let's maybe do some algebra, clean this up, make it look a little bit nicer. Particularly what I'm going to do is I'm going to take that x minus x1, that change in x, and I'm just going to slide it to the other side, multiply both sides by that change in x. So from here, we are going to get that y minus y1 is equal to m times x minus x1. All right. It's just the slope formula, except I've made it a little bit more generic, right? We're not talking about specific points anymore. This is a formula for any point on this line, not talking about specifics. And then I've also just done a little bit of algebra to make it look a little bit cleaner. And this right here is our point slope form. So this is the super scary, super daunting. No one likes to use it because there's so much memorization involved and it's just so ugly looking. Y minus y1 equal to m times x minus x1. But again, it's just slope. It's just slope, but I've shuffled around some of the numbers to make it look a little bit cleaner. Make it look a little bit more like a formula. And the advantage of using something like the point slope versus something like the slope intercept is it allows us to avoid scenarios where maybe the intercept is really messy. Oftentimes you receive problems where you find an intercept and it's nice, you get like +3 or -7, and that's fantastic, but that's not really how life works. There are an infinite number of possible intercepts, and this allows us to take this formula, allows us to work instead with any point that lives on our graph. So we get to pick and choose. We get to play with the values that work really nicely for us rather than having to fight through the slog of numbers that are potentially going to be messy and not very, very fun. All right, let's take a moment. Let's look at example 1 here, and then we'll get some practice with both of these forms. For example 1, we're being asked to determine whether what we are seeing is a linear function or not. So again, linear function, whenever you're being asked, is this function linear? Warning bells, whistles go off in your head. You are looking to see, can you pin down a precise slope that works for this particular function? Now, a very common pitfall, I want to focus here on 1C. A very common pitfall for this kind of question is to look at a table like 1C here and to go through and let's figure out what are our changes in y. So we notice first, from 13 to 28, we increase by 15. And from 28 to 58, we increase by 30. And there's an overwhelming temptation to say, aha, the amount that we have changed by has changed. Our rate of change is now different, right? Our change in y has doubled. And as a result of that, this function would not be linear. And that very well might be the case, but we are jumping the gun by only looking at the change in y. Slope is always a ratio of how much has our y changed per unit change in x. So you're never going to be able to approach these problems just by looking at just the change in y or just by looking at the change in x. You need to check that ratio between the two. In fact, what we find, the change from 5 to 10, that's going to be plus 5. From 10 to 20 is plus 10. Notice that this ratio of delta y, how much my y has changed per delta x, is staying constant at 15 over 5, or 30 over 10, or just 3. And so even though the delta y that we see is not constant, even though the delta x that we see isn't constant, the ratio between the two always is. This would be a linear function. So don't let the table that I throw your way that has weird y values, weird changes in y, weird changes in x, don't let that throw you off. You're always looking at how do the ratios between the two. For equations, I'd say it's maybe a little bit easier. Generally speaking, for equations, our goal is just to say, does it look like y equals mx plus b? Oftentimes it is, can we get it to look like y equals mx plus b? But sometimes that's not always so obvious. So looking, for instance, at e here, that negative quantity of, in this case, x minus 2 over 5 equal to 2y, trying to figure out, is what we see here a linear equation? Trying to get this into y equals mx plus b, very natural first step here would be to like solve for y. So maybe dividing by 2 on both sides. Dividing by 2 in the case of working with fractions is the same as multiplying the denominator by 2. So we would get here, for instance, that y is equal to negative x minus 3 over 10. And does this look like y equals mx plus b? It kind of doesn't, right? It's like one giant unified fraction going on here. And so if I asked you the question, like, what is the slope? What is the y-intercept? It's not necessarily super obvious how to parse it apart. Like, what is this actually look like? How is it going to behave? Things like that. And so while, yes, the core idea of trying to make things look like our y equals mx plus b isn't a bad one, you can certainly run into equations like this that are in fact linear, but don't quite look like y equals mx plus b. Okay, so what's maybe a better thing to look for than just does it match this formula that we have? What I would say is we want to look for, is there an x in the numerator, and is the power of the x 1? So notice here, x in the numerator, and the power is 1, no other x's. It's not like it's in the exponent, it's not in some weird like root, it is just in the numerator, power 1. This is going to be a linear function. even though it looks kind of weird. Okay, but if it's a linear function, that means it should have a way to write it as y equals mx plus b. And we've solved for y, so we should be relatively close to that. And in fact, we are. But what you have to do here is you have to take this fraction and break it apart into two separate fractions. So essentially taking that 1 over 10, distributing it through, and what you would get is that y is equal to negative 1/10 x plus 3 over 10. And here we can very much more clearly see, yes, in fact, we have a b. Yes, we have an m. Yes, we have a b. Much more clearly, this is going to be. Yeah. Why is it plus 3/10 instead of minus 3/10? That is a very, very good question. That is coming from the fact that we see this negative on the outside of the fraction. Think of that negative as distributing into both the x and the negative 3. And so you'll get a negative x and you'll get a positive. So essentially another way to write the numerator here would be to say that this is like negative x plus 3 all divided by 3 all divided by 5. It's the fact that that negative is on the outside there, which causes us some weirdness with the positive and negative. Another way to do it, which might make it look a little bit more clear, is to leave the negative on the outside, break apart the fraction. So this is negative, now in parentheses, 1 over 10 x minus 3 over 10. And then that negative is going to distribute it. Might make it a little more clear. Yeah, fair question. That one's deliberately again. Good question. Any other questions with example 1? All right. I want to look at 2A, and then I'm going to give you guys the rest of this time to work through that the 0013 classwork reminder due tonight, 11:59, quiz tomorrow, all that fun stuff. All right. So in this case, we are given different pieces of information. Sometimes it's tables, sometimes it's points, sometimes it's blah, 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 blah. Take that information and write out the equation for the line that would pass through, that would follow those kinds of instructions in both our slope-intercept and our point-slope line. We're going to start with point-slope and then work our way to slope-intercept. That's just generally, I find, a little bit easier. All right. So looking at A is like the bread and butter kind of baseline of what you should expect to be given at this level. This is like the least amount of information I could possibly give you. Try to find a line with it. All right. In this case, giving you that we have a line that is passing through 2 points, 1, 5, and 4, 11. What is the only piece of information that we're really missing here, though, in order to write the equation to our line? So we are definitely missing the y-intercept, but do we need the y-intercept for point-slope? No, we can have any point be our start point. That's kind of the advantage of point-slope form is we actually don't even need to know the y-intercept for this. So beyond the y-intercept, what other piece? I agree that we're missing that for sure. What other piece of information are we missing? We're missing the slope here. Okay, so that's a pretty good place to start. What is the slope going to be for this function? We say that m is equal to y2. It doesn't matter what you choose as y1 and y2, just be consistent. So for instance, if I say that 11 is y2 and 5 is y1, then 4 needs to be my x2, and 1 needs to be my x1. All right, and what do we find here? Well, what we find here is that this is going to be 6/3, or a slope of 2. That is actually all the information we need to fully write out the equation for this. Or actually, basically done. All right, we'll start with our point slope form. It does not matter which point you pick. It doesn't matter what was y1, what was x1. It doesn't matter what was y2, what was x2. Again, just be consistent. So for instance, here we might say that we're looking at y minus 11 is equal to 2 times x minus 4, and that is completely fine. Again, the advantage of point slope form, it doesn't matter where we start. It doesn't matter what that initial point is. We just need 1. But you totally could also have y minus 5 and x minus 1, and that would also work. That would also be completely fine. Okay, fantastic. If I was just asking you to write the equation of a line, we'd be done. I asked you to use both the slope-intercept form and point-slope form here, though. So a little bit more work to do, but really that is just solving for y and then doing a little bit of cleanup. Right, the cleanup in this case is going to be, we can distribute that 2. So 2 to the x, 2 to the negative 4. We get 2x minus 8. And then to solve for y, we're going to add 11 to both sides. So 2x minus 8 plus 11, I get that y is equal to 2x plus 3. And you should get 2x plus 3 if you had started with 1, 5 as well. You would get 2x minus 2 plus 5, which would give you that 2x plus 3. All right, questions for 2A? How are we feeling? Absolutely exhausted? No. Oh my goodness. That must be nice. Fantastic. All right. Couple of things to note again. 11:59 deadline. Get your thing submitted. Don't stay up till 3 in the morning. I had a student say, "Hey, I can get this in, but it's not going to be until like 3 in the morning." I said, "Please do not discard hours and hours of sleep to try and get this in." I am a fairly reasonable person most days. If you talk to me, I can certainly arrange something. But yeah, make sure you get that classwork in. Quiz tomorrow over just the 0, 0 through 13. So 0, 0, that is like classifying numbers. 1, 2, which was domains, ranges, is what I'm looking at a function. What is the, it's not going to be, I will go ahead and give you, we're not going to talk much about ranges, but like identifying domains of various functions, things like that. And then 1, 3, that increasing, decreasing, max, min, even odd. And I think I said yesterday, don't worry about piecewise for the quiz, but it is fair game for the test. All right, beyond that, you got about 20 minutes, a little less. Yeah. And we do have access codes now for Pearson. We are probably going to get that set up, not for this next assignment. Yes. Yeah, so which equation would we use the top equation? Top equation minus I agree, yeah, because -2 is less than 0, so we would use the top equation here. What about first?
I don't know why I thought you had.
The second equation.
First couple of years.
Perfect, right, yeah. That's good.
Like,
Yeah, it's just one
standard
file.
functions.
It should
HP body.
Yeah, absolutely.
Extra I could do to figure out what I'm doing, like besides just studying this.
Sure, like just like other
This
resources.
is the first day I stepped in here.
For sure. So the other resource that I kind of will always say is just